Good afternoon, everybody. Hope you guys are doing well. Today we're going to look at the limits of trig functions. And before we get into the actual limits, there's a couple of important things that we have to keep top of mind. And we've seen these things before. Some of them we've known for a while. Some of them we have looked at just at the beginning of this unit. So I just want to remind you of a few graphs that we looked at. One of them was y, whoops, I got to turn my pen on, y equals sine x over x. Okay, and I showed you this one on the very first day, and we're going to kind of see why. What actually happens is that at 1, we get a whole, which makes sense. Well, actually, x equals 0, I should say, and y equals 1. And we get a whole there, which makes sense because, we can't divide by 0. However, there is a limit there. Okay, and so this graph kind of looks like this. Okay, so we'll discuss why the limit as x approaches 0 of sine x over x equals 1. So that's one thing. We also looked at this graph, y equals the cosine of x minus 1 over x. And again, we're interested in what happens when x equals 0 because, again, we can't divide by 0. And what we saw graphically on the very first day of this unit is that there's, again, a whole at 0, but there is a limit there. And this guy looks something like this. Okay, so again, the limit as x approaches 0 of the cosine of x minus 1 over x is equal to 0. Okay, so although the value of the function does not exist, the f of 0 does not exist, the limit as x approaches 0 does exist. And that limit for this particular function is 0. Okay, and then the other two things I want to remind you of, which we've known for a while, is just the regular y equals sine x graph. Okay, and that looks like this, of course. Right, and it goes in this direction as well. Right, this is 1, this is negative 1, and this would be 2 pi. Okay, and here the limit as x approaches 0 of sine x is 0. Okay, that's just the value of the function. And here we do have a point there, right? F of x does exist when x equals 0. And then also the cosine function. If y equals cosine x, this is getting a little squished, then it looks like this. And again, this over here would be 2 pi. And that value, of course, is 1. Okay, so the limit as x approaches 0 of cosine x is equal to 1. Maybe I'll just try and do this so that I can partition these off a little bit for you. There we go. That's a little better, hopefully. Okay, so we're just going to try and keep those things in mind as we go through our discussion today. Okay. All right. So the first thing I want to introduce to you is something called L'Hopital's rule. And L'Hopital's rule is something that helps us to evaluate limits that involve indeterminates. So a reminder that an indeterminate is something that looks like this: 0 over 0, or infinity over infinity. And in fact, it can be positive or negative infinity over positive or negative infinity. So something like that. So a really good example would be the limit as x approaches 0 of x over x. Okay, because that limit is going to be 0 over 0. Okay, now we kind of should know what this is because x over x simplifies to 1. So although there's going to be a hole there in the graph, we know that this limit is 1. Okay, now L'Hopital's rule explains why. L'Hopital's rule basically says that if the numerator and the denominator of the limit are each functions. Okay, so in this case, if we look at this particular example, the numerator's function is x and the denominator's function is also x. And both of those are differentiable. I can differentiate the numerator and I can differentiate the denominator. Then the limit is the same as the limit as x approaches 0 of the derivative of the numerator over the derivative of the denominator. Okay, so if the limit as x approaches c of f of x equals the limit as x approaches c of g of x equals 0 or positive and negative infinity, and the limit as x approaches c of their derivatives both exist, then this is true. Okay, and that can really help us out, because in this case, what we can do is instead of plugging in a 0 for x and x here, we can say, well, that's going to equal the limit as x approaches 0 of each of their derivatives. Now, each of their derivatives are 1. And that's just 1. Okay? So, L'Hopital's rule can actually help us to understand why these two functions, y equals sine x over x and y equals cos x minus 1 over x, have the limits that they do. Okay? Because, in fact, they are both indeterminates. If we look at the value of sine x, the value of sine x when x equals 0 is 0. Okay, the value of cosine x minus 1, well, the value of cosine x when x equals 0 is 1. When we subtract 1 from it, that's going to make it 0, right? So these functions as x approaches 0 are going to be indeterminates. They're going to be 0 over 0. So we can apply L'Hopital's rule there to figure out their limits as x approaches 0. Okay? All right, so what we're going to do is we're going to evaluate some limits. And if we remember what these two graphs look like, and what I mean by these two graphs are this one and this one, and we remember that the limit as x approaches 0 of sine x over x is 1, and the limit as x approaches 0 of cosine x minus 1 over x is 0, then we can sub in a 1 for sine x over x or a 0 for cosine x minus 1 over x. So we can do that. Okay. If we don't remember that, then we can use L'Hopital's rule. And of course, we can do it both ways. Okay. Now, what I'm going to show you as we go through these is how to do it both ways. Okay. So let's say we're looking at this first one. Okay, and we're looking at the limit as x approaches 0 of sine x over 6x. Okay. Well, what we can do is we can take the 6 out sort of as a coefficient and write this as the limit as x approaches 0 of 1 over 6 times sine x over x. Okay. Now, if you remember that the limit as x approaches 0 of sine x over x is 1, then you can replace that with a 1. And this is going to equal 1 over 6 times 1, which is 1 over 6. Okay, so that's one approach. But you got to remember what the limit of sine x over x as x approaches 0 is. Okay, or we can use L'Hopital's rule. Okay, and we can say that the limit as x approaches 0 of sine x over 6x is going to be the same as the limit as x approaches 0 of the derivatives of both of these. The derivative of sine x is cosine x, and the derivative of 6x is 6. Okay, Now we don't have to plug in a 0 in the denominator, so we can actually just put a 0 in for x. Okay, and that's going to be cosine of 0 over 6. The cosine of 0 is equal to 1, so that's 1 over 6. Okay, so you can use L'Hopital's rule as well. Okay, now let's look at the next one. So this next one, if we try to use that trick with sine of 5x over x, we can't really do that because we would need to have, it would have to be sine x over, sorry, it would have to be sine of 5x over 5x, right? Whatever's here must be the same as what's here. Those two have to match in order for that limit to be a 1. Okay, now what we can do though is we can do some sort of algebraic gymnastics to make those the same. Okay, now if we want to do that, what we would have to do to get a 5, to basically get a 5x in the denominator is multiply the denominator by 5. And in order to not change the value of the limit, we'd have to multiply the numerator by 5 as well, because then we're just multiplying that limit by 1. Right? 5 over 5 is equal to 1. So this is going to become the limit as x approaches 0 of 5 sine of 5x over 5x. And now these guys match. And because those guys match, that limit is going to equal 1. And so we can now, we can now say that this is equal to 5, and that 5 comes from here, times 1, which is 5. Okay? Or, again, we can use L'Hopital's rule, right? So we can say the limit as x approaches 0 of sine of 5x over x is going to be the limit of the derivative of the numerator and denominator. So derivative of sine 5x, we got to use a chain rule there. So it's going to be cosine of 5x times 5 over derivative of x is just 1. Okay, and now we can plug in a 0 for x. So this is going to be the cosine of 5 times 0 times 5 over 1. Actually, I should put that in brackets like that. There we go. That's better. Okay, and then again, cosine of 5 times 0 is just 0. So that's cosine of 0 is 1 times 5 over 1, which is 5. Okay, so you get the same answer either way. All right, let's try another one. Okay, so here we've got the limit as x approaches 0 of sine of 9x over sine of 3x. So if we want to do that trick of using the fact that the limit as x approaches 0 of sine x over x equals 1, essentially what we'd need in the numerator is a sine of 9x over 9x. And so in order to get that, again, we need to do some algebraic gymnastics, if you will, okay? So if we want to have that, actually I'll do this down here maybe, right? Let's say in this numerator, we had something that looks like this. Whoops. Okay, and in the denominator we had that as well. Okay, well, the only way for me to achieve that is if I had multiplied this by 9x as well. Because then essentially, if you think about working backwards, the 9x's would cancel to just make sine of 9x in the numerator. Okay, so 9x times sine of 9x over 9x is the same of sine of 9x. okay? And similarly, if I want to have this sine of 3x over 3x, I would have to have 3x times sine 3x over 3x. So I can achieve that, but again, it takes quite a bit of sort of algebraic gymnastics to do that, okay? All right, so now what I'm gonna get, if we want to approach it this way, is we can now sort of break this into two separate limits, where we're gonna have the limit as x approaches 0 of 9x over 3x times the limit as x approaches 0 of sine of 9x over 9x over sine of 3x over 3x, right? And then here, these x's cancel. So this is just 9 over 3 is 3 times, this is going to be 1 over 1, which is 1. And that is 3. Okay, so that's one way of approaching it. The other way, right, we can also use L'Hopital's rule. Okay, so the limit as x approaches 0 of sine 9x over sine 3x will be the derivative of each of those, and that is the cosine of 9x times 9 over the cosine of 3x times 3. And we can plug, or sorry, I forgot limits. Sorry, let me just erase that and fix that. It's equal to the limit as x approaches 0 of cosine 9x times 9 over cosine 3x times 3. That's better. I can plug in a 0 now because the cosine of 0 is 1. And so I'm not going to have a 0 in the denominator. So this will become the cosine of 9 times 0 times 9 over the cosine of 3 times 0 times 3. And again, the cosine of 0 is 1. So that becomes 1 times 9 over 1 times 3, which is 3. Okay? All right. Let's do this one over here. Okay, so limit as x approaches 0 of 8 cosine x minus 8 over x. Okay, so one thing we can do here is you may notice that there's a common factor in the numerator of 8. So we could factor that out and write it as the limit as x approaches 0 of 8 times cosine x minus 1 over x. And then if you remember from the beginning of this lesson, the cosine of x minus 1 over x has a limit of 0. So this is going to be the limit, or actually we can actually just replace right now, right? This is just going to be 8 times 0, which is 0. Okay, so that's one approach. The other approach is L'Hopital's rule, and that is going to give us the limit as x approaches 0 of 8 cosine x minus 8 over x. That's going to equal the derivative, or the limit rather, as x approaches 0 of the derivative of the numerator and denominator. So the derivative of 8 cosine x minus 8 is negative 8 sine x. And then the derivative of negative 8 is just 0 over 1. And now I can plug in a 0 for x. So that's negative 8 sine of 0 over 1. And the sine of 0 is 0. So this is negative 8 times 0 over 1, which is 0. Okay, so again, we get the same answer. Okay, and then the last one. So this last question, there's no way in this question, the limit as x approaches pi of 4 sine x over pi minus x, there's no way to get a sine x over x or a cosine x minus 1 over x, right? There's no way to do that substitution because firstly, we're not approaching 0, we're approaching pi, right? And those limits are really only useful when we're approaching 0. And also in the denominator, our denominator isn't x, it's pi minus x. And so for this particular example, we really just want to use L'Hopital's rule. Okay, so the limit as x approaches pi of 4 sine x over pi minus x is going to equal the limit as x approaches pi of the derivative of each of these. So the derivative of 4 sine x is 4 cosine x over the derivative of pi minus x is just negative x. Sorry, not negative x. My bad. Negative 1. Negative 1. There we go. That's better. Okay. And now I can plug in a pi for x. So that will give us 4 cosine pi over negative 1. If you remember from your cosine graph, right, cosine looks like this. This is over here, 2 pi, so pi is right here. And the value of pi, the value of cosine rather, when x equals pi is negative 1. So this is going to be 4 times negative 1 over negative 1, which is just 4. All right. All right, so lots of options as to approach these questions. L'Hopital's rule is incredibly, incredibly useful, not just for trig functions, but for all types of limits. And so it will be something that you will revisit going forward into other math courses. And so, yeah, hopefully it's something that you'll use and that you'll practice. All right, guys, that's it for today. I will see you guys